Hi, and welcome to a video on optimization for Calculus 1. And in this section, we're going to talk about how to determine, for example, in an application problem, what our greatest profit might be, least cost, least time, greatest strength, optimum size, least distance, maximum distance, things like that. We are also going to do some geometrical examples, so we might also be talking about greatest area or least perimeter, etc. So we are maximizing and minimizing something, and that's what you're going to have to figure out in each problem. What am I trying to find the maximum or minimum of? Now, this first one is already complete, so you can kind of get a holistic view of what we're doing, and then we're going to dive into some examples together. So this first one is an example that says find two positive numbers such that their product is 192 and the sum of the first plus 3 times the second is a minimum. So I just let x equal the first positive number, and I did remind myself here that that number does need to be positive, and y equaling that second positive number. And I didn't, again, know at the beginning that they were 24 and 8. That's something where I just put my answers when I was done. So first thing that I did was write a relationship between my two variables because, again, we're talking about single variable calculus examples. So you want one variable in and one variable out. So right now I sort of have two variables that I'm talking about how they change, and I can only have one. So this relationship between the two variables, it says find two positive numbers such that their product is 192. There's almost a period or a stopping point in your problem after that statement. Their product is 192. That has nothing to do with anything changes or a rate of change or a derivative. That is a known fact. Their product is 192. So we write x times y equals 192, and then you can solve that relationship equation, that we'll call that, for either x or y. Then you come over and say I have a sum. So I have the sum of the first plus 3 times the second needs to be a minimum. So then I went over here to the right and I wrote my sum equation. Sum is x plus 3y. So, and what that really is talking about is just my first plus 3 times the second is some summation, some sum here. And this is where you can probably see a little bit easier. I'll highlight it in green for us so you can see what I'm talking about, where I have two variables being put in and one variable out. So that's why we have to go back to that relationship equation that we wrote, solve for either variable. In this case, I solved for x, and substitute that in. And then that way we now have s as an equation in one variable. So s is a function of y, for example. S could have been a function of x, or my s for sum could have been a function of y. It doesn't really matter. So now you can find s prime, and or you can find s prime of y if you'd like to label it that way, or ds dy. But because we're minimizing, right, we want that sum to be a minimum, we know that we can find that minimum or the potential minimum once that first derivative is 0, because remember, a min or a max or one of those turning points, if I have some curve, happens at these horizontal tangents or turning points or when your first derivative is 0. So I found my first derivative for s, set it equal to 0. This gives us all the possible places where I will have a maximum or minimum. And then I have to determine which one fits my problem. So which one is the minimum and not a maximum. And also my problem asked for find two positive numbers. So I kind of already know which one it is, but I would check that for sure. So I just did a simple first derivative number line test here, but I really only tested the positive 8 because I don't think negative 8 was a possibility. Put a number in less than 8 into S prime, it is negative. Put a number greater than 8 into S prime, it is positive. So I can see that indeed 8 would be a minimum value, and 8 was the y value, so that's why I put that back up into where I identified my variable. And then if y is 8, x is 192 over y, so 192 over 8 would be 24. Okay, so let's take a look at maybe a little bit more geometrical of an example. Let's do some distance. Okay, now when most people read this next question, they don't actually read it for technical knowledge and to interpret what it's saying. They just start with, ooh, I'm going to find the derivative and set that derivative equal to 0, etc. So let's really look at what this is asking us to find here. It says find a point on the graph of f of x equals x squared that is closest to 2 comma 1/2. So if I just sort of give myself a sketch of what's going on here, I can quickly sketch f of x equals x squared, something like so. And then what I want you to make sure you realize is that this point 2 comma 1/2 is not on this curve, right? The point on the curve if x equals 2 would be 2, 4. So this is at 2 comma 1/2. So 2, so 1, this would be a 1, right? So 2 comma 1/2 is approximately right here. Okay, so and again, maybe that's a little bit far away from 1, but that's a good, approximation or estimate here. So find a point on the graph of this curve that is closest to this point that is not on the curve. So closest is a term that we actually use for minimum distance. Right? So I want to minimize the distance between the curve and that point. So I'm going to actually use distance formula here. And I want to minimize distance, so that means I'm going to find the derivative of the distance formula, not necessarily of this f of x function. Okay, so I'll write down the distance formula. Most of you recognize the distance formula probably like so here. You see what's going on? Okay, so here's my distance formula. I, on the other hand, like the distance formula, whether you do capital D or lowercase d doesn't really matter here. I like looking at the distance formula a little differently, like change in x squared plus change in y squared. So if you've ever seen it like that before, that's the same thing as well. So it doesn't matter where you go from here. We're going to say that this distance is between the curve and the point. So I at least know that the point has to be there. So I'll put the point in. So x minus the 2 quantity squared and y minus the 1/2 quantity squared. And again, you could have said that this was 2 minus x or 1/2 minus y, but I like that the variable stays positive. I just think it's easier to multiply out, and if I ever need chain rule for derivatives, that's just a little bit easier to work with. And now again, here's the part where you have two variables in your equation and one variable out. And we are in single variable calculus, so I need to take care of that. So I need a relationship between x and y. Well, I want the point always to be on that curve. So this is the curve y equals x squared. So that is my relationship between x and y. So in place of the y, I will put x squared. So everything else is going to stay the same here, except for in place of y is x squared. Okay? And now I'm actually ready to say I have a formula, right, for distance, and it's in single variable calculus. So I have, only x's over here. So d is a function of x. So I'm ready to take its derivative. Now, you may want to multiply, things out underneath that square root and combine like terms. That might be something that you find this derivative is easier to take in that form. So I'll go ahead and do that so you can see it. So it'd be square root of, this would be x squared minus 4x plus 4. And just be careful when you square this. This will be x to the fourth minus 1x squared plus a fourth. Okay. And if I combine like terms, I have the square root of, let's see, positive x to the fourth. X squared minus x squared adds to 0, so minus 4x. You can add 4 and 1/4, or you can literally just write plus 4 plus 1/4. I know that's 17/4, but you can leave it because, again, the derivative of 4 is 0 and the derivative of 1/4 is 0, so it's not going to really impact your problem at all. So you don't always have to work harder, right? You just have to work smarter and be more efficient. So again, if you just put plus 4 plus a fourth, that's fine too. So this derivative is going to be a function of x. So again, I can look at this all to the 1/2 exponent. So I can bring down this half, keep my base the same, all to the negative half now times the derivative of what's inside, which is 4x cubed minus 4. So when I look at this d prime here, it's really 4x cubed minus 4 over 2 of the square roots, x to the fourth minus 4x plus 17/4. If I rewrote that d prime just using my radical instead of that negative half, this is what it looks like. And the reason I did that is so now when I set this equal to 0, hopefully you can see that my numerator needs to be 0. And whether you divided that by 2 or not is insignificant, right? Because I'll end up with the same answer here. So 4 equals 4x cubed. So 1 equals x cubed. So x equals 1. And when I reread the question to make sure that I am actually answering the problem, it does say find a point on the graph of f of x equals x squared. So I go back to my graph or go back to my function, and if I have x equals 1, I know what that point is. So if x is 1, y is x squared. So y is 1 as well. So it's the point 1, 1 will minimize the distance to 2, comma 1/2. Okay. So they were looking for that point 1, 1. So I'm going to show you one other thing about distance because there is a little bit more efficient way to find this derivative and to minimize this distance. So let me show you that real quick. Okay, so if we go over here just to the side, I'm just going to give you another option. So instead of going through what we did here where there was just a little bit maybe more algebra to work with, instead of minimizing this distance formula, you can minimize the square of the distance and come out with the same answer. So let me show you that. So I will square both sides. Okay, so this will become d squared. So now it's just this polynomial. Again, if I had the plus 4 plus a fourth, that would have been fine. So now I can take the derivative of both sides, so this will be d squared prime equals 4x cubed minus 4, and I can minimize this, set that equal to 0, and hopefully you can see that I'm at the exact same place I was at over here at x equals 1. And maybe that's just a little bit easier of algebra for you. So instead of minimizing the distance, you can also minimize the square of the distance and you're going to get the same result. So that might help you in future problems. So we're going to talk about something now that I think is difficult for people just purely because they don't remember all of their formulas for these. And then also I think you get caught up in some of the numeric manipulation in this case. So let's look at this one. The sum of the perimeters of an equilateral triangle and a square is 10. That is a static statement, right? That first sentence. The sum of the perimeters of an equilateral triangle and a square is 10, period. That has nothing to do with anything changing. So that's going to be my relationship between my variables. Then it says, find the dimensions of the triangle and the square that produce a minimum total area. So I'm going to be using that then to write some equation for total area. And that's what I want to minimize. I want a minimum total area. All right, so let's say, just for consistency's sake, that x is the sides of a square and y are the sides of the equilateral triangle. I know that I need perimeter of these and I need area, okay? So I'll talk about first I have the square and then I have the equilateral triangle. Okay? So if my sides of the square x and the sides of my equilateral triangle are y, again, I don't know if those visuals were 100% necessary, but they're there. So the perimeter of that square would be 4x, and hopefully the area of that square being x squared is not a stretch. But this is something that I'm not sure that we are familiar with, is the area maybe of this equilateral triangle. So the perimeter of this equilateral triangle, not a big deal, 3y, but I'm not sure that we remember the area. So this is square root of 3 over 4y squared. So real quick, I'll just show you, if I have an equilateral triangle, that's a 60-degree angle. You probably recognize the 1/2 base times height formula for area, so I'll work off of that. So the base is going to be a y, right, the whole base. When you drop this perpendicular, it does become a perpendicular bisector, so that is now 1/2 of y, and this is 1/2 of y. And so if you have this right triangle right here, this is a 30, 60, 90. So if this is 1/2 of y, this height would be rad 3 over 2 times y. And if you multiply all of that out, you do get that rad 3 over 4 y squared. Okay, so we can figure it out. I sort of was told to memorize it kind of as the 2, 3, 4. So y squared, rad 3 over 4. I don't know. Or you can just set it up like so and figure out the 1/2 base times height and figure it out that way. So we're going to use these in all of our calculations so that we can just refer to those instead. So the first sentence talked about the sum of the perimeters of these being 10. So I'm going to add up 4x plus 3y equals 10. And I'm also going to note that this is my relationship between the two variables that I can use. So I will probably need to solve this equation for either x or y so that I can write my minimum total area function in terms of one variable. I don't have to decide which variable right now. I can decide that at a later time. Okay, so now we're going to write, it says find the dimensions of the triangle and the square that produce minimum total area. Okay, so my areas are going to be x squared plus square root of 3 over 4y squared. And this is where you get to pick, do you want to solve this relationship equation for x or y and substitute in the other one? A lot of people already feel like for some reason this y squared term is complicated enough. I'm not sure really why, because that square root of 3 over 4 is just a coefficient. So a lot of people will maybe decide to solve for x. That's fine. So I'll subtract 3y and I'll divide by 4. And you can write these separate or together. That is entirely up to you. So I'll go over to my area equation and I will say instead of x, 10 minus 3y over 4 all squared plus red 3 over 4y squared. And really, I think you've done probably the hardest part. There's a little bit maybe, again, some numeric computation in here that might get a little tricky, but because we're going to try to keep it exact here. But overall, I think you've got the idea. So you have to, at some point, I now have area as a function of y, one in, one out, so that's perfect. I now just have to find the first derivative. So again, at any point, I can do that. And then I have to set this equal to 0. I'm ready to find the first derivative right now. If you're not comfortable with that, you can square this binomial and look at those individual terms. That's up to you. But I'm ready because I know chain rule, so I'm going to say a prime, because again, that's eventually going to go to 0 anyway. So whether you say dA dy or a prime of y, doesn't matter. So I'm going to use chain rule here on this first one, bring down my exponent, keep my base the same, times the derivative of what's inside. So just be careful. It's not just negative 3, right? Because this would be 10 over 4 minus 3 over 4 times y. So my derivative of what's inside is negative 3 over 4. Okay, plus, bring down your 2. So this will be square root of 3 over 2 times y. And I will set this equal to 0 before I do anything to this. So I can at least do that. So I have 10 minus 3y, I'll just leave this for one step here, over 2 times negative 3 over 4 plus red 3 over 2y. Now, if you didn't want to deal with fractions at all, now would be the time to get rid of them. U equals 0. So you could multiply both sides, for example, by 8 if you wanted to do that. You can multiply, it's a little bit big, but I could just multiply by 4 and then see if something reduces. It doesn't look like it's going to. So I'll just multiply everything I see by 8. So 0 times 8 is still 0. This would divide to 1, so I just have the 10 minus 3y times negative 3 left, plus 4 rad 3 times y. So I'll distribute that negative 3, so it's negative 30 plus 9y plus 4 rad 3 times y. And this is a linear statement, and again, this is where sometimes people have a little bit of difficulty. These are both just linear y's, y to the first power. So in normal times, if it was 9y plus just 4y, I could combine like terms and say that that's 13y. But I can't add a 9 and a 4 rad 3, but I can factor out the y, and then I see the 9 plus 4 rad 3. They are both coefficients of y. And then I will add the 30 over to the other side so that I can divide both sides by the 9 plus 4 rad 3. Seems like a decently ugly number, which is why I was saying we're going to have a little bit of work to do now that we are going to have to find the other side. So if I look back at the original question, it does say find the dimensions of the triangle and the square. and y was the side of my triangle. So sides of equilateral triangle are 30 over 9 plus 4 rad 3. And then now I need to figure out what are the sides of the square. So I do have this equation right here that will sort of automatically solve for x, so I will use that. It's going to be a complex fraction though, because my y is a fraction and it's inside of a fraction. My y is 30 over 9 plus 4 rad 3. Okay, so that's 10 minus 90 over 9 plus 4 rad 3 all over 4. And again, sure, this is an exact answer, but complex fractions usually are not allowed to be left, and this does actually combine decently. So what I like to do is I like to just multiply everything by a factor of 1. So I'm going to multiply the numerator by 9 plus 4 rad 3 and the denominator by 9 plus 4 rad 3. It will save me, it's virtually kind of the same thing as getting common denominators, but it's going to save me one step in this complex fraction. So I'll distribute that. So 9 plus 4 rad 3 times 10 would be 90 plus 40 rad 3. I do have to distribute that 10. And then I have minus just 90 because this 9 plus 4 rad 3 divided by 9 plus 4 rad 3 will be a 1. So it's just 90 all over 4 times 9 plus 4 rad 3. And again, I don't usually multiply out denominators like that until someone tells me I have to. But what I'll notice in this case is 90 minus 90 add to 0. And then I can divide 40 by 4. So the sides of the square, 40 divided by 4 is going to leave a 10. So 10 rad 3 over 9 plus 4 rad 3. Again, these are not the decimal versions. These are keeping them exact. I don't know that the calculus from the beginning was tricky. I think that sometimes we get into numerical problems where we feel maybe a little bit uncomfortable, and this may be one of those examples. Okay, so let's look at this next problem here. So if 1200 square centimeters of material is available to make a box with a square base and an open top, find the largest possible volume of the box. So first of all, 1200 square centimeters is the amount of material that you have to make the box. So that is a known amount, and that's going to give us that relationship that we talk about in every problem. So I'm going to write out relationship. And then what we know is that that's called surface area of a box, well, I'll just say, is 1200 square centimeters. So my dimensions of my box are also going to be represented in centimeters. So then I will look at this and say, okay, what would the surface area of the box formula be? Surface area is going to be adding up all the sides that you have, all of those areas on the outside. So if you have a square base, that's the bottom of it, and then you're building up, right, sides from that. So let's say this is what my box might look like. So this might be x by x, but then it's going to be y high. So I'm going to have 4 sides, if you will, that are all x by y, right? 1, 2, and then the left side, and then the, let's say, bottom side. So I'll have 4 sides that are all x, y. And then I will have one base here that's x by x, or x squared. But it says an open top, okay? So there's only one bottom, there's not a top. So there are only 5 sides to this box, the 4 that kind of go around, if you will, and then the bottom. And that surface area equals 1200. So this is my relationship that relates these variables. And again, I don't have to necessarily solve for a variable right this minute. I will usually go to what am I trying to maximize or minimize. So I am trying to find the largest possible volume of this box. So I know a volume of a box to be the area of the base, which in this case is x times x, or x squared, times the height. That's going to give me how much it's going to take to fill that box, for example, x squared y. So I can solve, this equation really however I want. I think x is going to be much more difficult. My point in waiting is that if I could have easily solved, for example, for x squared, I don't need to go all the way in solving for x. So what I mean by that is, see how I have an x squared in this other equation. I know I have an x over here, so that's going to cause me that problem. But if I didn't, and if that term was just a 4y, I could easily solve that equation for x squared. I don't have to go all the way down to solving for x. And I'll show you that on the next example as well that we work through. So I don't think I want to easily solve this equation for x because x is in both terms. I'm going to solve this for y. So this is 1200 minus x squared, and then I will divide everything by 4x. Okay, so y is 1200 divided by 4. I could say that this is 300 over x minus 1/4 x. So if you think that's going to be an easier way to write it, you can, or you could have just left it as 1200 minus x squared all over 4x. When you go to substitute, you'll probably see a preferred substitution. So in place of y, I'm going to now substitute one of these for y. They're of equal probably levels of difficulty for me. But you might just say, you know what, this one, I can see that the x squared divided by the x, will divide out, or maybe you like distributing this way better. So I went through the separation, so I'll leave it as 2 separate terms. But I will distribute that x squared so I don't have to use product rule or anything when I find this derivative. So this will just be 300x minus 1/4 x cubed. And that should make sense to you that if you write your volume in terms of a single variable, volume is 3 dimensions, so that does make sense to me that I have an x cubed in there. So volume is now written as a function of x, right? 1 in, 1 out. So I'm ready to find volume's derivative. So v prime, 300 minus 3/4 x squared. And then I can set that equal to 0 to either maximize or minimize. So 300 minus 3/4 x squared. I will add 3/4 x squared. Again, you can multiply at any time if you don't like working with that fraction. I'm going to multiply both sides by 4/3. So I have x squared equals 400. So x is really plus or minus 20. And so I want to make sure I'm answering the question here. It says find the largest possible volume of the box. So I'm not finding the dimensions, I'm finding the volume. Well, my volume equation was x squared y. Or you could go back to this 300x minus 1/4 x cubed if you just wanted to put it in there. Okay, it's entirely up to you. Since I have my x, I think that's probably where I will go. So I'm going to put it back in there, and I'm going to say that volume in terms of single variables, 300x minus 1/4 x cubed, and I now know that my x should be 20 because I don't think a side length and a volume of negative 20 is going to help me very much. So I'm going to use the positive 20 for that side length. So 300 times 20 minus 1/4 times 20 cubed. And I'll let my calculator help me. So I'm just going to type in 300 times 20. I know what that is, but I'm just going to let it go. Minus 1/4, so 0.25 times 20 cubed. MAT220 is your cubed, if you wanted to use that. So 4,000. So find the largest possible volume of the box. So max volume is 4,000 cubic centimeters. Remember, we were in centimeters, so that's cubic centimeters. Now, especially since I had options for my x, positive and negative 20, let's make sure that on a number line test, right, a first derivative test, that positive 20 is a maximum, right? So what I'm going to do that is kind of think of that first derivative number line test here. So if I go to y equals, and I'm going to type in the first derivative that I found, which was 300 minus 0.75, because it was 3/4 x squared. This is the formula for the derivative of it. And I know that I'm getting x equals 20 as an answer. So I'm going to look all the way out to, let's just say 40. And I also know that my y values are going to be decently big. It's a parabola for v prime, but I can probably see it, negative 10 to 10. Let me show you what I'm looking for here. So wherever x equals 20 happens, right, which is that right there, I can calculate a value, if you don't believe me, at x equals 20. That should be my 0. To the left of 20, right, so if I trace to the left of 20, you're seeing positive values. That's all I need to know. I really can't see them on my graph, right? 13 isn't shown, but I'm tracing on my function here. And then if I go to the right of x equals 20, I see negative values for y. So what that tells me is I have positive values on v prime and then negative values on v prime. So I was increasing followed by decreasing, so that is indeed a maximum. So I do know that that is my maximum volume and not my minimum volume. Especially when you have choices for x, you really want to be sure that you're picking the right one and that it's even possible. You know, sometimes an answer to a math problem might be, oh, that's not possible with that much material, right? And you want your base to be a square, for example. Maybe your answer is that it is not possible within those constraints to do what you want to do. So let's take a look at just one more. Okay, so in this one, we are making a cone out of circular paper for a local fish and chips vendor in London. So the circular paper has a radius of 5 inches, so I drew that on the circular piece of paper here. And we're going to cut a wedge out of it as shown, and then when you actually force these two pieces to come together, this will form our three-dimensional cone. This bottom point that I'm drawing in the center of my circle becomes the very bottom of that cone. And then the 5 then becomes the outside slant height or edge of the cone. So I do not know this perpendicular height or how tall my cone is. I only know the slant height in this case is 5. So if I only gave you this information right here, I could say find the maximum volume of this cone. Okay? That's all you need. So how would we do that? Well, in most of these problems that we've written or that we've solved, we've started with what is the relationship between my variables for this problem. And in this case, I'm going to use R, H, and 5. And if you look at it, I hope you can see, and that's why drawing these becomes so important sometimes, that my relationship between my variables comes from the Pythagorean theorem. R squared plus h squared should be 5 squared, or 25. And again, I can solve this for r squared, h, or h squared. I'm not sure yet which one I want to, so I leave that alone for now, and now I talk about what I want to maximize or minimize. I'm trying to maximize volume in this case, so I'm going to write the formula for volume of a cone. And that volume, we should all know from related rates, is 1/3 pi r squared h. And again, from related rates, we understood the idea, hopefully, that we had two variables in, right, a radius and a height, and one variable out, which was volume. So we really want to write our volume in terms of one variable, so we have single variable, but we don't necessarily care whether it's volume according to radius or volume with respect to height. We will write that based on our relationship that we are given. So I go back over to my relationship, and what I hope you can notice here is that your formula has an r squared for volume, and your relationship has an r squared. So I can solve my relationship equation for r squared. Again, I don't need to solve all the way for r. If this is how much r squared is, I can put that in place of r squared in my volume formula, because r squared is the same thing as r squared. So r squared is 25 minus h squared. So my volume equation, you can write this as pi over 3 or 1/3 pi, whatever you're comfortable with. And then I'll distribute that h in there, 25h minus h cubed. And again, because it's volume and it's three-dimensional, it kind of makes sense to me that I have a variable cubed when I put it all in terms of single variable. All right, so I have a good volume equation, so let's find volume's derivative. So v prime, or v prime of h in this case. 1/3 pi is a coefficient, so that's going to stay. And then the derivative of 25h is 25, and the derivative of h cubed is 3h squared. So again, I don't know that you'll find any of these single derivatives to be the difficult point of the problem. So I'll set this equal to 0. I'm not going to change anything yet. I'm just setting it equal to 0. And again, when you're testing for maximum and minimum, you want to make sure that you're looking at the right equation. So I'm just going to box here my volume equation and then my volume's derivative equation, so I always know where those two are. So if I set my volume derivative equation equal to 0, I can divide both sides by this 1/3 pi, or multiply both sides by 3 and then divide by pi, but then it's gone. So 0 equals 25 minus 3h squared. So I'm going to add 3h squared to the left-hand side and the right-hand side. Divide by 3. And take the square root. So technically, h is plus or minus positive 5. Square root of 25 would be 5 over square root of 3. You can leave it as square root of 25/3 if that's easier for you. Now, I really think it's going to be the positive 5 over square root of 3, because again, we're talking about a physical height of a cone that we're trying to make. But I would absolutely suggest testing that. So if we did, again, a v prime number line test, I'm only going to put the positive 5 over rad 3 on here, and I would test it to make sure that we are finding maximum volume. So you would want to see that your function is increasing and then decreasing, or in other words, you would want to see that your v prime is positive and then negative, like I showed on the previous one. I would just use my calculator for that. Now, we have to make sure we're answering the question. If I just say, oh, well, the height that would maximize this volume is 5 over square root of 3, that's great, but that doesn't answer the question. Find the maximum volume. So I have to go back to my volume equation and put that height in there. Now, you can go back to the basic volume of a cone, the 1/3 pi r squared h. You can go back to where it's just all in terms of h. It's entirely up to you. I actually think in this case, because I have a good relationship function over here for r squared, so I know r squared will be 25 minus h squared, and I know h squared is 25 thirds. So r squared, this would be 75 thirds. So r squared is 50 thirds. So that wasn't hard for me to find. So since I know my volume was 1/3 pi r squared h, r squared is 50 thirds, and h is positive 5 over square root of 3. So that wasn't very hard for me to figure out r squared and h, so I just like this formula better. So 50 times 5 would be 250 pi over 3 times 3, so 9 square root of 3. And this would be inches cubed, right? Because it was 5 inches in the original problem and we're volume, and so this would be my max volume. Again, given the constraint that my radius of my original paper, my Pac-Man looking paper here that I'm going to cut out and create a cone with, had to have a radius of 5 inches. So given that, I can then find what that max volume would be. So I hope you found these optimization problems to help you sort through how to set these up and how to find what you're trying to find. The relationship and really pausing and reading your problem and figuring out what is that relationship between the variables if needed. For example, if you wrote the volume and it only had one variable in and one variable out, you don't need a relationship because you already have single variable calculus, so you can just find the derivative and set it equal to 0 to maximize or minimize. But for many of our problems, we are in multi-dimensions or we have multi-variables in there, so we have to write that relationship so that we can then go back to single variable. So I hope you found this helpful on optimization, which can be a tricky subject for some students.